So yeah, last time we talked a lot about transforming between Cartesian to polar, polar to Cartesian, all that sort of stuff. Today, we're kind of the second day on 10.3. We're just going to be considering polar equations and graphs and all that sort of stuff in their own rights. So we're not going to be so much transforming back and forth between these things. And so the big kind of new thing that we get in today's class is all about tangent lines. So here's where we got it in the pre-class notes. It's using the exact same formula that we got when we were talking about parametric equations. So that is, if you want the slope of the tangent line, well, you calculate out the rise divided by the run. And so now you have to kind of change your thinking a little bit here. Now we're going to take our parameter, again, just a fancy name for a variable. So, right, our parameter, instead of being t, right, we're going to use thetas. So after all, this is going to be polar stuff. And so I wouldn't recommend, memorizing this equation here. I know if I tried to memorize this, I'd definitely get something wrong. You'll see that kind of just whenever you come across a problem, we'll parametrize it and we'll just kind of use our whole dy d theta on top, the rise, dx d theta on bottom, the run, in order to come up with the slope of the tangent line. So it won't actually be this bad. Again, wouldn't recommend memorizing this here. So that's going to be the big stuff for today. Let's go ahead and take a few questions here before we jump into our new problems. Aditya, you have the floor.
Hi, can you hear me?
Yeah, sure can.
Cool. So when we're sort of creating equations from in 3.10.3, we're trying to get equations from, I guess, like polar to Cartesian, right? So if there's a situation where it's like r cosine of like 2 theta or like 3 theta, is there a way we can convert that into like the values of x and y? Or is it like, do we have to use one of the trig identities or something like that?
Yeah, I would recommend using a trig identity. So to rewrite that using like the double angle theorem or something like this.
Oh, okay. I was hoping there was a shorthand, to be honest.
No, I'm sorry, not so much.
All right, thank you.
Yeah, no problem. Good. Any questions in the Q&A, Yuan, that we should talk about?
No, except the ones asking the MASH 234. What professor do you recommend?
Oh, I don't know who's teaching it over the summer. I'd have to take a look at the list. So maybe after class, I could take a look at that, or maybe before Monday's class. Good. So let's go ahead and start thinking about our problems for today. Oops. Scrolled a little bit through that. So here we are talking about polar graphs and tangents. And so the first thing here, a fun true and false question. The polar equations r equals sine of 2 theta and r equals negative sine of 2 theta have the same graph. And so, okay, let's go ahead. Well, obviously they don't have the same equation, right? One's positive and one's negative. But in order to check and see if they actually have the same graph, maybe we could plot a few points at least to give us some intuition about this. Obviously, if they're not lining up, the points aren't lining up, then we can just say it's false very fast. So let's go ahead. Maybe this one, by the way, I'm going to call this R1, right? So my first function, I'm going to call this just R2 here. So I'm going to go ahead and plot a few. We'll start off with 1, and if we need more points, we can plot more of them. Well, I don't know. Why don't we try just like pi over 6? So if I plug in pi over 6 into this, and let's go ahead, maybe draw some axes here. So pi over 6, we're going to get sine of pi over 3 and for R1. So sine of pi over 3, well, that's going to be root 3 over 2. And if we do the same sort of deal for R2, right, well, it's going to be pretty much the exact same, but we're going to get the negative answer, negative root 3 over 2. So that is, if I'm pointing in this direction, in the pi over 6 direction here, oops. The first function says we need to go out, some positive number of steps. So I'll go ahead and maybe do this one in blue or so. Maybe it's out here. And the second function, this R2, says we need to go some negative number of steps. It's the same number of steps, but it's backwards. And so at least with this, it seems like they're giving out different points. And so maybe we'd be tempted to say that they're not the same graph. But actually, right, when we're looking over in the pi/6 direction, there's one more opportunity where you could, right, you could have a purple point, the second graph here, could actually still hit this point when it's not looking in the pi/6 direction. Can anyone tell me what direction should we be looking at where we give, these things one more opportunity to actually line up on top of one another? And so let's go ahead. I see there's a couple of different votes here. I got one vote for a negative pi/6, and I got one vote for a 7 pi/6. So let's see, in the negative pi/6, right, that would be kind of like this direction here. So notice you're going to be somewhere along this line, so you wouldn't actually get another opportunity to hit those same points there. But actually, I like the 7 pi/6, right? So if you do 6 pi/6, that's a full pi there, and then you go pi/6 more. That's going to be 7 pi/6. Then you're going to be pointing in this good direction, and you have one more opportunity in order to kind of hit these points here. And so why don't we go ahead and plug these things in? So 7 pi/6. And if I do that here for my first one, let's see, this is going to be sine of 7 pi/3. 7 pi/3. Let me draw a mini unit circle here, because it's been a little while for this. 7 pi/3. So here's 1 pi/3, 2 pi/3, 3 pi/3, 4, 5, 6 pi/3. That's 2 pi. Okay, that makes sense. And 7 pi/3. So at sine of 7 pi/3, this is √3/2. So when I'm looking in the 7 pi/6 direction, right, I need to go out this √3/2. So this is again for my R1. So you can see actually I'm lining right on top of this other point. Okay, so this gives me a little bit of hope. What about for the other one? So if I was to plug this in for R2, my second graph here, well, of course it's going to be the exact same, but it's going to be the negative of this, right? Oops, I should probably actually plug in my point. So 7 pi/3. And so when I do this, I'm going to get negative √3/2. And we can see actually that these 2 points, when we consider them both together, right, they do actually line up on top of one another. And so now I'm thinking this may actually be the same graph. Before I maybe spoil the surprise, and if anyone would like, you can click on this link here. But let's go ahead and take a quick question before we spoil this. Go ahead, Jeff.
Thank you, Professor. I was just on a true false like this. Can we assume that we're doing the full theta rotation at 360 degrees to form the graph?
Yes, unless if there's any restriction on the domain for theta. Technically, you not even do like 0 to 2 pi. You just let theta run indefinitely.
Okay, thank you.
Yep, no problem. Good. And so let's go ahead and see, like, if I wanted to show this in general, notice what's happening here is that they're not actually lining up at the exact same places. But we have that once you've rotated it by 180 degrees, right, we're actually going backwards in order to hit the point. So that is kind of, we're making some relationship between maybe our normal r theta versus if you were to go ahead and add 180 degrees to your theta. Now you're looking in the opposite direction. If you also move backwards, then you can hit the same point. And so I would like to go ahead and maybe take my R2 here and see what happens if I plug in negative R and theta plus 180 and see if there's any reason to believe that these would actually line up. So again, instead of R, I'm going to put negative R. And instead, oops, I forgot. This is supposed to be R2, by the way. And instead of theta, I'm going to go ahead and do theta plus 180. And so, okay, the negatives will cancel out. And we get to 2 theta plus 360. Well, we know that going 360 degrees around the circle, right, you're going to get back to where you started. So adding 360 doesn't change the value for sine whatsoever. And so you can see that when we go ahead and swap in, instead of this negative, instead of just r and our regular theta, when you swap in negative r and this theta plus 180, you can see that you actually do get the exact same equation as r1. So these are hitting all of the same points, but they're just hitting it at basically different times, at different theta values here. Let me go ahead and see if, this, well, I'll pull up this graph here. We're about to be switching over and looking at Desmos anyway for a second. So maybe we can talk about example 13, and then I'll kind of bring up all of these on my desktop computer, just because it's a little bit of a pain to switch back and forth between the desktop and the iPad here. All right, so one more quick question here. Ian, you have the floor, and then we'll start thinking about example 13, and I'll also pull this up in Desmos so you can kind of see that yes, they are hitting all the same points, just at different theta values.
Oh, so was 360 eliminated because it was the same thing as 0, kind of, or?
Exactly, because with the circular functions, sine and cosine, they repeat themselves every 360 degrees. So I should be careful here. I was using degrees. This is a little bit weird. I should probably, Yuan's probably cringing. Why are you doing calculus with degrees? Really, we should be adding pi. Let's have a 2 there. So pi, this should be plus 2 pi, right? When you do calculus, you really ought to be doing radians. And so, yeah, if you go 2 pi around the circle, right, you're going to get to the same point as if you didn't do that rotation, right? And so that's why these are equivalent.
Gotcha. Thank you.
Yeah, definitely. Good. So again, we'll kind of showcase what this looks like, or if you want to type this into URL, I tried to click on it. Apparently I didn't make it an active URL, but we'll take a look at that kind of when we're also doing example 13 here. So this right here, example 13, it becomes much more important, especially in 10.4 when we're determining arc length of polar equations and areas with our polar equations, to be able to trace a graph once and only once. Because if you're tracing it more than once, then of course your arc length is going to be, well, because you've already traced the shape and you're doing it several times, we're going to be adding undue length. And likewise with areas, right? You just want to add up the area once. And so you want to be able to trace these things once and only once. And so I have these 4 equations here that I'd like you to spend 60 seconds, maybe, not too long, trying to guess, right? What's the interval for theta where each one of these is graphed once and only once? And then we're going to go ahead and check these things in Desmos. So I'll shut up for 60 seconds or so, give you a chance to write down some guesses, and then we're going to go ahead into Desmos and check if our guesses are good. All right. I don't know about you guys, but if I was taking guesses for these, because sine repeats itself every 2 pi, and the fact that we're kind of going, 2 pi around in a circle here, I'd be tempted to say, darn near all of these are going to be, like 0 to 2 pi. Maybe for this one with the sine of 2 theta here, maybe I would try like 0 to pi or something like this. I have no idea what to guess for this one. I don't know. We'll just try 0 to 2 pi, right? But again, our goal is to kind of guess and check. And overall, we want to graph these once and only once. So let's go ahead, and I have Desmos up on my desktop. Let's go ahead and pull this up here. By the way, so here is that link. So this has the sine of 2 theta. You can see you get this nice 4-leaf clover sort of deal. And we can go ahead and check. And, I'm going to run my different points from 0 to 2 pi. And you can kind of see this point get traced. It traces out the curve as you run it from 0 to 2 pi. If I was to change this now to negative sine of 2 theta, notice that, well, the graph did change, but it was exactly the same. It's all of the same points. Now, if I go ahead and run this, remember kind of how it ran before is that it went up this first loop like this, and then kind of down and around, and it kind of ran in general kind of clockwise direction. But then within each one of these little leaves, it was going counterclockwise. Let's go ahead and see, right? If I was to run this time or this theta value forward now, what happens? So you can see it starts in the third quadrant instead, rather than in the first quadrant. So that's kind of the fact that you're hitting these points at different times or at different theta values here. So again, that's kind of what this one looks like, starting off in the third quadrant and going around. And this one here, when we just had positive, it starts off in the first quadrant and goes around. All right, so that's kind of what this is looking like here. Now let's go ahead and sketch our particular things. So my first one here was 2 plus sine theta. So 2 plus sine of theta here. Looks like I need to maybe zoom out. And I just have this going from 0 to 2 pi. Let's go ahead and hit play and see if we trace it once and only once. So yes, it looks like we traced it exactly once. So this one, it does turn out to be 0 to 2 pi. Okay, if we were to just change this a little bit and do 2 sine of theta, 2 sine of theta. So we can see I have a bit of a smaller circle up here. If I was to check and see if 0 to 2 pi traces this once and only once, let's take a look. Not so much. It looks like it actually traced it twice. So it traced it twice. So let's check. If I was to do 0 to pi here, it looks like this would go, yep, around just once. So this one here, 0 to pi, you actually get the full picture. If you go any further, again, you're going to be duplicating all of the same points. Well, let's check, right, when I did this, and we already did this one. We kind of know what this already looks like here. So let's go ahead, and if I do 0 to pi, you can see that I only trace half of it. So this one is actually going to be 0 to 2 pi here. Let's double check. Got all the way around, so make sure it hits every point once and only once. That looks great. So yes, this one is also 0 to, well, this one's 0 to 2 pi. I had written down 0 to pi here, so I was wrong on this one. I was also wrong on the previous one, right? And then there was this last bit here, this 3 theta divided by 2. Oof, this is looking interesting. Notice that actually when I wrote this, Desmos went ahead and changed this. This top one here is now going from 0 to 4 pi. I just guessed 0 to 2 pi. If I was to do 0 to 2 pi, notice that I only have half of this. So there's more picture that's not being included when I just do 0 to 2 pi. If you do 3 pi, you get even more. If you do 4 pi, you get even more. And now if you do like 5 pi or 6 pi or 7 pi, right, you don't get any more picture. So this is going to be 0 to 4 pi here in order to hit all of these points. So let's go 0 to 4 pi and run this. Oops, there we go. And so this is how it generates this curve. So this one is actually 0 to 4 pi. All right, let me go ahead and switch over and get my iPad back in on this here. And in the meantime, if anyone has any questions, now is an excellent time. So I've changed my answers to be the correct answers. That way, if anyone's looking at this, you know, after class, they're not getting the wrong things. Gabriel, you have your hand up. Go for it.
Yes, Professor. So my question is without using Desmos, how would we able to derive that answer? How would we able to come up with that solution?
Excellent. So yeah, the big thing here that I want us to take from this, and especially moving into 10.4, which is still a couple days away, but that it's dangerous to just guess that things, you know, you hit all of the points once and only once if you go 0 to 2 pi, right? And so really, we need to graph this out. And so kind of what we did at the beginning of 10.3, where you know, made tables and you plotted lots of points, that's really the surefire way of doing this by hand. Now, of course, if you have a homework assignment or whatnot, or something where you can use technology, sure, you can have Desmos help you. And we use Desmos here in order to kind of speed up the process, just because it does take a while to, you know, plot lots of points. But also we know this when it comes to like quizzes and exams and everything, is that it does take a while to plot all of these points. And so, of course, we are careful about the questions that we put on quizzes and exams for exactly that reason. Does that kind of make sense?
Yeah, that makes sense. Thank you.
Super. Yeah, definitely. Any questions in the Q&A, Yuan?
I think it's the same question. He wants to explain the 4 pi. How do you get the 4 pi?
Okay, yeah. So, I mean, you would need to graph this out. And when you do, you see that you don't actually have all of the points. And if you were to continue farther, you do continue to collect new points. So yeah, as soon as it starts kind of overlapping and you get the same curve, just repeating itself, then you can stop. But it's not so easy to guess this, right? Good. Why don't we go ahead and move on? And the big kind of new thing for today are these tangent lines, right? And so I'd like to showcase, this is a relatively nice one here. In fact, we already, in the previous problem with Desmos, we graphed 2 sine theta. And here we have 4 sine theta. And so if we go ahead and we plot some of these points, you could probably even guess it's going to be a circle kind of on the top here. But let's just kind of verify. And I'm going to plug in some different theta values. From the last one, we saw that you'll get the entire picture once we go up to pi. So if you go any further than this, you won't actually generate new points here. And so let's at least graph 0 pi, pi over 2. Let's do pi over 4 and 3 pi over 4 as well. These will be our theta values. And we can plug those in. And well, let's see, if we plug in 0, if we plug in pi, this is going to give us r is equal to 0. If we plug in pi over 2, well, sine is going to be 1. So multiply that by 4 and you get 4. And if we have pi over 4 that we input into sine, remember that's going to be root 2 over 2. So this is going to be giving 2 root 2 once we multiply it by 4. Sine of 3 pi over 4 is also root 2 over 2. So once you multiply it by 4, you get 2 root 2. And just kind of to recall, when we graph these things, it's good to use some approximations. And so root 2 is around 1.4. So these are around 2.8. All right, so when I'm facing off in the theta equals 0 direction, I have to take 0 steps. If I'm facing off in the pi over 4 direction, I have to take 2.8-ish steps. If I'm facing in the pi over 2 direction, didn't get a straight line there, but okay, I need to take 4 steps. If I'm facing in the 3 pi over 4 direction, I need to take this 2.8 steps again. And if I'm facing in the pi direction, I need to take 0 steps. So these 4 points right here become my graph. Remember, we could also plot more points, or you could convert this into Cartesian in order to really emphasize that this is indeed a circle. It's a circle of radius 2 that's been shifted up a bit. Okay. The rest of part A here says, what points does it appear that we have vertical tangents or horizontal tangents? So I'm going to say that we have some vertical tangents. I'll go ahead and do these in red. Maybe about right here and here. Maybe I've just, got lucky with those points, or maybe that this isn't quite an accurate graph, but based on my sketch anyway, right? Maybe it actually goes out a little bit farther or so. In someplace else is supposed to be like over here is supposed to be a vertical tangent. But from my sketch anyway, it looks like those are where we get vertical tangents. For horizontal tangents, it looks like here at the top of the circle and at the bottom of the circle, these are where we have horizontal tangents. Okay, and so we're of course going to want to verify this, not just with the graph and looking at it and saying, well, if my graph's accurate, then this is good, but if my graph's not accurate, then not so much, right? We want to be able to use the equations in order to come up with vertical and horizontal tangents. And so our first step is going to be writing some parametrization, right? This is really 10.1 and 10.2 sort of stuff, but here our parameter is going to be theta rather than t. And so what I'm going to go ahead and do is, well, we know x in polar form is going to be r cosine theta. And on this curve, right, we know what r is. R is given by 4 sine theta. And so, well, instead of r, I'm going to go ahead and plug in 4 sine theta everywhere I see an r. And so if I want my equation for x, my equation for x looks like, well, r cosine theta. So 4 sine theta cosine theta. So now we can see that we have x as just a function of thetas. Likewise, we can get y as just a function of thetas. We know in polar that y is r sine theta. And we can go ahead and substitute in everywhere I see an r, I'm going to put 4 sine theta. After all, on this curve, that's what r is equal to. And so we get 4 sine theta times sine theta. You can, of course, simplify this down, and this is going to be 4 sine squared theta. Okay, now we're going to go ahead and use this parametrization here to verify our guess. So that is, we're going to calculate out our dy dx. And remember, in order to do this, we're going to calculate out, just as we did in 10.2, we're going to do our rise stuff. So how much does y change as our parameter changes? So instead of t here, remember, we're using theta. And how much do we have for run, right? How much does our x change with regards to theta? And so we're going to go ahead and take those derivatives, the derivative of y with respect to theta and the derivative of x with respect to theta. I think I'm going to need a little bit of room here. So, okay, the derivative of y with respect to theta, that's on top there. So if I take the derivative of this, well, the 2 needs to come down. We reduce our power by 1. So instead of sine squared, we're going to get sine to the first power. And then I need to multiply by the derivative of the inside. All right, that one wasn't so bad. How about our derivative of x with respect to theta? Well, this one here, right, we have a product rule, right? There's a product of 2 functions. So we do have to be a bit careful with this, and we need to use the product rule. So it's going to be the derivative of the first times the second plus the first times the derivative of the second. So there we go. And now thinking back to, before in 10.2, when we were doing all these, right, we talked a little bit about horizontal and vertical tangents. And the big thing that we took away from then, right, is if you didn't have any run, so, right, if dy dt was equal to 0, and that is thinking that your run, this is our rise, our change in y. So thinking that our rise is equal to 0, that means that you're going to have a horizontal tangent. And likewise, if you don't have any run, that is your dx dt is equal to 0. So that is your run is equal to 0. This implies that you're going to have a vertical tangent. So we're going to take each one of these things actually, and you can see that this full equation here is excellent if we wanted to calculate out the slope of the tangent line at a particular point. But because we're interested in vertical and horizontal tangents, really we're going to be setting, the numerator equal to 0 and the denominator equal to 0 in order to figure out when we have horizontal and vertical tangents. So if I go ahead, and now we're, by the way, leaving the world of calculus and going into the world of algebra, and we're trying to solve 8 sine theta cosine theta. When does this equal 0? Right? So I took my dy dt. Remember, I wrote this in the context of 10.2, but now that we're in 10.3 and our parameter is theta rather than t, really you should be thinking of these as, dy d theta and dx d theta. So basically whatever your independent variable is, whether it's t, whether it's theta, that's what you should have there. And we're going to set those equal to 0. So dy d theta equal to 0, and we have to solve this. And so, okay, well, there's lots of places where really, right, if you have two things multiplied together and give out 0, well, if either one of those is 0, we know the result will be 0. So this will give stuff like, in the realm of when does sine of theta equal 0, this would be things like 0, pi, 2 pi. Of course, you could go negative as well, but all of these would be legitimate options. And for cosine, right, where does it equal 0? This would be things like pi over 2 and 3 pi over 2, 5 pi over 2, all that sort of stuff. Again, kind of going on forever sort of deal. However, we see that kind of with our graph, since it starts repeating itself after pi, right? The only distinct places on the graph where you have, horizontal tangents is at 0 and at pi over 2. You could also kind of argue maybe we should include pi, but again, this is really at the same spot, right? So if you're looking in either the 0 direction or in the pi direction, remember you're down here at this point. If you're looking in the pi over 2 direction, right? Remember when we plugged in pi over 2 into this, we were up here at this point. So again, our goal was to guess our answers from A. So again, we did get at these points at 0 and at pi over 2, these are correct. So again, the other ones are going to be same points. Same points as theta equals 0. And these ones right here are going to be same points as theta equals pi over 2. Okay. Now we need to solve this bottom one. When does this equal to 0? And that's maybe a little bit more difficult. There's several different ways that we can do this. Let me go ahead and set up my equation again. So we're going to have 4 cosine squared theta minus 4 sine squared theta is equal to, and again, that's our x derivative there. And if we want there to be a vertical tangent, that means we shouldn't move to the left or the right at all, right? So our run should be 0. So we can go ahead and maybe rearrange this a little bit. And we're going to get cosine squared theta is equal to sine squared theta. Notice I also divided by 4 there. And then we could even take the square root if we wanted here. And so if we take the square root, we're going to get, well, either cosine is going to be equal to sine, or, right, whenever you take a square root, you need to have a plus and a minus, right? So the other option is maybe cosine is equal to negative sine. And notice that if you squared either one of these, you would get the equation cosine squared is equal to sine squared. And so everything else would work out. And so from this, right, again, you could rearrange this and kind of solve for tangents and all that sort of stuff. But actually looking at these, I can think about, I know some places on my unit circle where this is true. For instance, at theta equals pi over 4, they're both root 2 over 2, right? So the cosine of theta is equal to the sine of theta, right? They're both root 2 over 2. And likewise, well, this isn't unique. There are lots of other places, right? For instance, at 5 pi over 4 and at 9 pi over 4. And just like before, these are all going to be repeats. right? So I'm going to kind of forget about these just because they're repeats. And in particular, we got all of our values on our curve as we went from 0 to pi. So all of these are beyond pi, right? 5 pi over 4, 9 pi over 4, those are all bigger than pi. Likewise, for the negative value here, right? I know that in the second quadrant, there's a place where they're both root 2 over 2, but one of them is negative, right? They're off by a negative. And so this is going to be at 3 pi over 4. And likewise, there are other places where this equation is satisfied, right? Like at 7 pi over 4 and 11 pi over 4. And you can do negative values of theta as well and all that sort of stuff. But again, the only unique point here is going to be at 3 pi over 4. And so indeed, we do get exactly those that we thought, right? At pi over 4, when we're looking in this direction, we do get a vertical tangent. And at 3 pi over 4, when we're looking in this direction, we get a vertical tangent. And so we were able to confirm our guesses. It turns out our picture was halfway decent, right? And so these were correct. Good. Any questions with this here? Let me go ahead and scooch this on to one page. There we go. Ian, you have a question. Go for it.
Wait, did you just use test points to figure out if they worked or not?
In order to solve at this last point here, I thought about my unit circle and thought about when sine is equal to cosine. So yes, that was kind of test points. The other way that you could do this is you could divide by cosine on both sides, and you could think about when does tangent equal 1, and that is also at theta equals pi over 4.
Oh, okay.
Either way, you get the same result.
Gotcha. Thank you.
Yeah, of course. Good. Any questions in the Q&A, Yuan?
Isn't sine positive at 3 pi over 4?
Isn't sine positive at 3 pi over 4? Yes, it is, but cosine is negative, right? And so they are off by a negative sign. So right, when you plug in 3 pi over 4 into this, you would get negative root 2 over 2, and that's the same as the cosine value at 3 pi over 4. So they would be equal once you include the extra negative bit. Good. So let's go ahead and maybe showcase. Here's one that I think would be maybe reasonable length for possibly a quiz or an exam. But we're going to go ahead and sketch a little bit. Of course, if you wanted to sketch all of this, this is very difficult. And so it just specifies, right? Do a sketch on the interval from 0 to pi over 3. Then we're going to go ahead and find the equation of the tangent line, not just the slope, but the full-on equation of the tangent line at pi over 6. All right, so let's go ahead and plug in some points here. Theta values, R values. I want to go from 0 to pi over 3. Let's see, I could also plug in something like pi over 6 to help me out with my picture. But notice also that we're multiplying by 2 here before we apply cosine. So this allows us to plug in some values that we normally can't with our unit circle. So for instance, if I wanted to do pi over 12, or here if I did, well, pi over 4, really what I'm thinking there is 3 pi over 12, which just happens to be pi over 4. So let's go ahead and verify, that we can go ahead and plug these in and actually get out results that we know on our unit circle and everything. So for instance, well, okay, 0. If I plug in 0 into cosine, I'm going to get 1. So 4 times 1 is going to be 4. So all the way out here, if I'm looking in that 0 theta direction, I need to take 4 steps from the origin. All right, when I'm looking in the pi over 12 direction, which by the way is half of pi over 6, so we're going to be looking in this direction right here. Let's see, this is going to be 4 cosine of, well, 2 times pi over 12 is going to be pi over 6. Notice that that is a value on our unit circle, so we can evaluate this. Cosine of pi over 6 is going to be root 3 over 2. And so times 4, this is going to be 2 root 3. Remember, root 3 is around 1.7-ish, so this is going to be approximately 3.4. So 3.5, a little bit less than that, 3.4 there. If I was to look in the pi over 6 direction, so up in this direction, we're going to have 4 cosine of pi over 3 once we've multiplied by our 2 there. And cosine of pi over 3 is going to be 1/2. I don't need the approximately, it's just equal to 2. So I need to go out 2 here. If I was to look in the pi over 4 direction, this would be 4 cosine of 2 times pi over 4 is going to be pi over 2. A cosine of pi over 2 is 0. So who cares about multiplying by 4? You get 0. And then finally, let's go ahead and do at pi over 3. So at pi over 3, this is going to be 4 cosine of 2 pi over 3. So thinking about 2 pi over 3, this is going to be the negative 1/2. And so multiply that by 4, you're going to get negative 2. So when I'm looking in the pi over 3 direction, up in here, I need to go negative 2. So backwards by 2. So we're just going to kind of connect these points here. And this right here is a piece of our curve. By the way, we have seen this one already in Desmos. This is, if we were to continue, this is going to be a 4-leaf clover, by the way. So this is what it fully looks like. But again, we're only really interested on this interval from 0 to pi over 3. Our goal is to find the equation of a tangent line at pi over 6. So at pi over 6, this point right here, it's hard to say from my picture that, maybe that this is a place where the tangent lines, the slope is actually 0, but maybe it's close to 0. Maybe it's a little bit positive, right? Depending on how my sketch is, or maybe it's a little bit negative, right? It's hard to say, but it's pretty close to 0 there. So this is the point that we become interested in for finding the equation of the tangent line. Okay, for the equation of the tangent line, remember these things always look like y minus some y point is equal to m times x minus some x point. That's an equation of our tangent line. And so we can get some of this without using any calculus, right? In particular, we can find the x naught, y naught without using any calculus. So let's go ahead and maybe do that really quick. So in order to solve for the x point, remember x is going to be equal to r cosine of theta. And so if I was to plug in my specific r value, this is going to be 4 cosine of 2 theta. And to that r, we need to multiply by cosine of theta. And so remember, we're very interested about what's happening at pi over 6. And so if I plug in theta equals pi over 6, this is going to give me the x value of, let's see, 4 and cosine of, 2 pi over 6. Well, that's the same thing as pi over 3. Cosine of pi over 3 is going to be 1/2. Cosine of pi over 6 is going to be root 3 over 2. And so this ends up being root 3. Okay, so now we know what our special x value is that corresponds to a theta value of pi over 6. Let's also figure out our y value, and then I see that there's a raised hand, so we'll call on some folks if there's questions. So again, I'm plugging in everywhere I see an r, I'm plugging in my specific equation for r. And now remember the equation for y goes r sine theta. So I'm going to go ahead and include a sine here. So at my special theta value, again, we want to know what y value corresponds to that. And so, okay, again, we have 4 and 2 times pi over 6 is going to be 1/2. And then sine of pi over 6, this is also going to be 1/2. And so we get out 1 here. And so this is what my special y point is going to be. So in fact, at these, now we know these, we go and input these in, y minus 1 and x minus root 3. So this is everything that we can achieve without any calculus. Now, when it comes to the slope of the tangent line, that's when we need to use the new stuff for today. Let's go ahead and take a quick question though. Anito, you have the floor.
So quick question. So when we have our x and y is equal to r and cosine and sine theta, and we have that like separate equal sign, whatever. So
Yes.
Are we basically using substitution from our original equation for our r value of 4 cosine 2 theta?
Exactly.
Into, like, the cosine and sine and whatever.
So yep, basically wherever we see an r, we swap out our specific polar equation.
All right, for sure. Oh, okay, that makes more sense. I was just confused. Thank you.
Super, yeah, no problem. Good. So let's go ahead and now take some derivatives and we'll calculate out the slope of our tangent line. So remember, the slope of the tangent line is always given by dy dx. When we learned about, in 10.2, how to do this for parametrized curves, we got this dy dt is what we called it back then, divided by dx dt. This is, again, the rise over the run with respect to some parameter. And now we're using thetas for our parameter rather than t's. So, but again, we're going to be taking some derivatives. And in this case, we're going to be plugging in some specific value, pi over 6. So we do have to be a little bit careful when we take our derivatives. Notice that I have already calculated out x with respect to theta and y with respect to theta. But notice that both of these are a product of functions. So when I go to take derivatives of them, I have to use the product rule. So let's go ahead and do that now. So derivative of y with respect to theta. This is going to be fairly long here. So we have the derivative of the first. So when I take the derivative of cosine, I get negative sine, leave the inside alone, multiply by the derivative of the inside. That's the chain rule. So that's the derivative of the first times the second plus the first times the derivative of the second. There we go. And now the derivative of x with respect to theta. Derivative of x with respect to theta, well, again, I need to use the product rule. So I take the derivative of the first, and very similar to last time, we have to use the chain rule and all that good stuff, times the second plus the first times the derivative of the second. And the derivative of cosine is going to be negative sine. So that right there is my slope equation. And this is good for all thetas and everything, but of course I'm very interested in when theta is equal to pi over 6. So everywhere I see a theta, I'm going to be plugging in pi over 6. By the way, before I do this, and this will be kind of where we finish up for today, I just wanted to remind you that we have not once had to use the memorized version of this, right? Technically, we are using this, right? And you can see that there's a sprinkling of sines and cosines and all that sort of stuff that of course come from, right? We input instead of our specific function. But that's what I said, that you really don't need to memorize this. And if I tried to memorize this, I would definitely screw something up about where the minus sign is or sines and cosines and all that sort of stuff. So again, I would recommend, please don't memorize this. Just once you have an equation, just think about it logically, right? And just kind of, take your derivatives, do the rise over the run, all that good stuff. All right, let's go ahead and finish this one up. Let's see, I'm going to have -8 and sine of pi over 3. That's going to be root 3 over 2. And sine of pi over 6, that's going to be 1/2. Let's see, +4 cosine of pi over 3. That's going to be 1/2. And cosine of pi over 6, that's going to be root 3 over 2. That's my numerator done. In the denominator, let's see, I have -8. And let's see, sine of pi over 3 is going to be root 3 over 2. And cosine of pi over 6 is going to be also root 3 over 2. And next up, oops, I have -4. Sine of pi over 3 is going to be 1/2. Sorry, cosine of pi over 3 is going to be 1/2. And sine of pi over 6 is going to be also 1/2. And so, okay, if you're entering this into WebWork or whatnot, it would technically take this. I would recommend maybe simplifying a little bit. All of this division by 2s will cancel with a lot of these 4s, which is quite nice. So at very least, I would write down -2 root 3 plus root 3 divided by negative, let's see, the 2s and the 8s cancel a little bit. There's still a 2 there. Ooh, and root 3 times root 3, that's going to be 3. And here we get -1. And so actually, this isn't bad at all. Negative root 3 divided by, let's see, -6 minus an extra 1 is going to be -7. All of those negatives will cancel out. And that right there is the slope of our tangent line. This is exactly what I would plug in everywhere I see an M. What was it? Root 3 over 7, I believe. Yeah. So the equation of the tangent line ends up being this right here. And with that, we can also see that my picture maybe wasn't the best, right? Root 3 over 7 is, it's nowhere near 1, for instance. It is kind of a small fraction there, but this is a little bit positive, right? We couldn't quite get that from my sketch. that this is actually, it's increasing there. It has a positive slope. We couldn't exactly see that from my picture. All right, so that is where we will call it for today. Stick around as always if there are any kind of one-on-one questions. Otherwise, have a great weekend, guys, and we'll see you next time. Remember, we're starting with 8.1 next time. 8.1 arc length in Cartesian coordinates. So that's Monday's class. Please watch those videos before coming to Monday. And as always, I'll post the rest of the solutions that we didn't get to later on D2L today. All right.